National Electrical Code Article 210.19 addresses branch circuits and connections to the high leg of a three-phase, four-wire delta system, which is where you find the 208 volts potential. The code specifically states that branch circuits shall not be connected between the high leg, sometimes called the wild leg or stinger leg, and the neutral or grounding conductor. The main reason behind this regulation is the voltage imbalance inherent in this type of system. In a typical three-phase, four-wire delta system, two of the phases are center-tapped, providing 120 volts from each phase to neutral and 240 volts phase to phase. However, the third phase, the high leg, provides approximately 208 volts to neutral. This 208 volts isn't a standard voltage that equipment is typically designed to use with a grounded neutral. Connecting standard 120 volts or 240 volts equipment to this 208 volts source can lead to overheating, malfunction, and potential safety hazards. The prohibition in Article 210.19 is there to prevent accidental connection and ensure equipment operates within its designed voltage range. Now, there are a few exceptions and specific applications where using the 208 volts from the high leg is permissible, but these are very controlled scenarios. Firstly, if you have equipment specifically designed and rated for 208 volts operation with a grounded neutral, it can be connected to the high leg. This is rare, but some specialized motors, lighting ballasts, or industrial equipment might be designed for this configuration. Secondly, in some industrial settings, auto transformers or other voltage adjustment devices might be used to derive a suitable voltage from the high leg for specific equipment. However, these installations must be carefully engineered and comply with all relevant code requirements, including proper overcurrent protection and grounding. Thirdly, it's crucial to understand the marking and identification requirements for the high leg. The NEC mandates that the high leg conductor be durably and permanently marked by an orange outer finish, or by other effective means. This marking must be visible throughout the electrical system, including at every point where a connection is made. This is to prevent accidental connection to the wrong voltage source. Now let's delve a bit deeper into the technical aspects of the three-phase, four-wire delta system and why the high leg voltage is what it is. Imagine a three-phase transformer with three separate windings, each producing a sinusoidal voltage. In a delta configuration, these windings are connected end-to-end, forming a closed loop. To create the four-wire system, one of the windings is center-tapped and the midpoint is grounded, becoming the neutral. This grounded center tap is what provides the 120 volts for single-phase loads. The voltage between the two ungrounded phases that are part of the center-tapped winding is 240 volts. However, the voltage between the high leg and the neutral is not simply the sum or difference of the other two voltages. It's derived from the vector sum of the voltages in the delta configuration. Using trigonometry and vector analysis, you can calculate that this voltage is approximately 208 volts, specifically 120 volts multiplied by the square root of 3, which is about 1.732. This 208 volts potential exists because of the phase angle difference between the voltages in the three windings. Each phase is 120 degrees apart, and this phase shift creates a unique voltage relationship in the delta configuration. Now let's consider some practical examples to illustrate the importance of adhering to Article 210.19. Imagine a scenario where an electrician, unaware of the high leg voltage, connects a standard 120 volts receptacle to the high leg and neutral. When a 120 volts appliance is plugged into this receptacle, it will be subjected to 208 volts, which is significantly higher than its designed operating voltage. This will likely cause the appliance to overheat rapidly, potentially damaging its internal components and creating a fire hazard. Another example is connecting a 240 volts motor intended for a standard three-phase delta system to the high leg and another phase. While the motor might initially seem to operate, the voltage imbalance can lead to excessive current draw in one of the phases, causing the motor to overheat and eventually fail. This is because the motor windings are designed for balanced voltage, and the high leg introduces a significant voltage asymmetry. Furthermore, it's crucial to consider the impact of the high leg on ground fault protection. Ground fault circuit interrupters, or GFCIs, are designed to detect small imbalances in current between the hot and neutral conductors, indicating a potential ground fault. However, the presence of the high leg can complicate ground fault detection, especially if there are unintentional connections between the high leg and ground. These unintentional connections can create circulating currents that interfere with the GFCI's ability to accurately sense ground faults. Therefore, careful attention must be paid to grounding and bonding practices in systems with a high leg to ensure proper ground fault protection. In addition to Article 210.19a, there are other related code sections that address the safe and proper use of three-phase, four-wire delta systems. Article 408 covers switchboards and panel boards, and it contains specific requirements for the arrangement and identification of busbars in these enclosures. The high leg busbar must be clearly marked to prevent accidental connections. Article 450 addresses transformers, and it outlines the requirements for overcurrent protection and grounding of transformers used in delta systems. Proper transformer protection is essential to prevent damage from overloads or faults. Article 250 covers grounding and bonding, and it contains detailed requirements for grounding the neutral conductor in a three-phase, four-wire delta system. Proper grounding is crucial for safety and to ensure that ground fault protective devices operate correctly. Furthermore, it's important to be aware of any local amendments or interpretations of the NEC that might apply in your jurisdiction. Some local authorities might have additional requirements or restrictions on the use of the high leg voltage. It's always best to consult with a qualified electrical inspector or engineer to ensure compliance with all applicable codes and regulations. Now, let's shift our focus to the specific types of equipment that might be rated for 208 volts operation. As mentioned earlier, some specialized motors are designed for this voltage. These motors typically have different winding configurations and insulation ratings compared to standard 240 volts motors. They are specifically designed to tolerate the voltage imbalance inherent in the high leg system. Lighting ballasts are another type of equipment that might be rated for 208 volts. These ballasts are used in fluorescent and high-intensity discharge lighting fixtures. They are designed to convert the 208 volts input voltage to the appropriate voltage and current required by the lamp. However, it's crucial to ensure that the ballast is specifically rated for 208 volts and not for some other voltage, such as 277 volts. Using the wrong voltage ballast can lead to premature lamp failure and potential safety hazards. Industrial heating equipment is another area where you might encounter 208 volts rated equipment. Some resistance heaters, ovens, and other industrial heating devices are designed to operate on this voltage. However, these devices must be carefully selected and installed to ensure proper operation and safety. The heating elements must be rated for the specific voltage and current, and the control system must be designed to regulate the temperature accurately. In conclusion, while the NEC generally prohibits the use of the 208 volts from the high leg for standard branch circuits, there are exceptions for equipment specifically designed and rated for this voltage. It's crucial to understand the code requirements and to consult with qualified professionals to ensure safe and compliant installations. Always prioritize safety and adhere to the NEC and any local amendments. Remember to properly identify and mark the high leg conductor to prevent accidental connections. When working with electrical systems, it's always best to err on the side of caution and to seek expert advice when needed. Electrical safety is paramount, and understanding the nuances of three-phase, four-wire delta systems is essential for qualified electricians and engineers. Also, remember that the information provided here is for general guidance only and should not be considered a substitute for professional electrical advice. Always consult with a licensed electrician or electrical engineer for specific applications and installations. The NEC is a complex document, and it's constantly evolving to reflect changes in technology and safety practices. Staying up to date on the latest code requirements is essential for anyone working in the electrical field. Understanding the fundamentals of three-phase power and the characteristics of the high leg is critical for safe and efficient electrical installations. By following the code and using best practices, you can ensure the safety and reliability of electrical systems for yourself and others. Finally, remember to always disconnect power before working on any electrical equipment. Lockout and tagout procedures should be followed to prevent accidental energization. Electrical work can be dangerous, and it's important to take all necessary precautions to protect yourself from harm. Always use appropriate personal protective equipment such as safety glasses, gloves, and insulated tools. If you're not comfortable working on electrical systems, it's best to leave the work to a qualified professional. Your safety and the safety of others should always be your top priority.